So let us talk about infrared thermal imaging. Now, what are electromagnetic waves? Water and sound waves transfer energy from one place to another. So they require a medium through which to travel. So they are mechanical waves. Electromagnetic waves is emitted whenever an electric charge is accelerated. So matter is largely composed of electrically charged particles that are continuously in motion. Hence, this electromagnetic radiation is continuously emitted by all objects. So electromagnetic waves do not require a medium to travel. They travel as vibrations in electric and magnetic fields. The speed of electromagnetic waves is speed of light, 3 into 10 to the power 8 meter per second. So light takes 8 minutes to move from sun to earth, that is 150 million miles at this speed. So this is how this electromagnetic waves are generated if you have electric and magnetic field. So light waves, classical theory describes light as a wave characterized by your amplitude, frequency and wavelength. So energy of a wave is proportional to the amplitude square. And quantum theory describes light as a particle. So light is a wave also and it is a particle also. In terms of particle, it is called a photon, which is having an energy which is given by E is equal to hn or nu. This is the frequency. This can be written as h into c by lambda. So this is known as the dual nature of light, the duality of light. It can be wave also, it can be particle also. So is it light a wave or a particle? So on large scale, we can treat a large number of photons as a wave. For subatomic phenomena, we often deal with a single few photons. So in case light is treated as a particle. So subatomic phenomena, we consider it as a particle. But on large scale, we consider it as a wave. So for explaining operations of photodetectors, we use the particle nature of light, this nature. For this, we don't take it as a wave, we treat it as a particle. Semiconductors, building block of these photodetectors. So band theory of solids. Solids are crystalline in nature, and energy levels of single atoms do not apply to solids. When a large number of atoms are brought together, they slip and these levels split into nearly contiguous energy bands. So there may or may not be an energy gap between energy bands. So electrons occupy these bands based upon the energy they possess. This is the form energy level to energy band. This is the separation of items in terms of energy, and this is the separation of atoms in terms of energy when the energy gap is there. So band theory of solid, the last filled or partially filled band is called the valence band. So the empty band above valence band, this is across the energy gap, which is called the conduction band. So the difference in energy between the valence band and the conduction band, this is the valence band and the conduction band, is known as the energy gap, e.g. for a particular material. So semiconductors, conductors and insulators. In conductors, this valence band is partially filled, and VB and CB they overlap. Valence band and conduction band overlap. While in the semiconductor, VB valence band is full, and the gap between the filled VB and CB is small, very small, right? While in the insulator, the valence band and conduction band, this difference is quite large, 5 eV. So in this conductor, electrons are free to move in partially between this VB and CB, and electrons jump. In the case of semiconductor, electron jumps from this VB to CB when they get enough energy from photons or thermal energy. And in this insulator, electron cannot move unless given a large amount of energy to jump from VB to CB. So conductor always conduct electricity like metals. Semiconductor conducts small amount of electricity at room temperature like germanium and silicon. And insulator, they do not conduct electricity like carbon. Carbon does not conduct electricity. So these are the type of semiconductor. We have intrinsic and extrinsic. Semiconductors are classified into these two forms. Intrinsic means it is a pure semiconductor crystal with no impurities, and such conductors have no charge carriers at this temperature. So at higher temperature or due to illumination, electrons are excited and cross the gap, the band gap to the conduction band, that is finite conductivity at room temperature. This is the silicon atoms, electrons in covalence band. An extrinsic semiconductor, the extra carriers created in semiconductor by introducing into the crystal some impurities, which is called the doping. So when a dopant create extra electrons, that is a negative charge, it is type N type semiconductor. And when the doping create extra hole, it is called a P type semiconductor. So by doping, the crystal can be altered so that it has a predominance of either electrons or holes. So this is the detector classification. These are IR or infrared detectors. They can be thermal or uncooled. They can be photon or cooled. Thermal or uncooled, photon or cooled. In this thermal or uncooled, they are pyroelectric, bolometer and thermopile. And in case of photon or cooled, they can be photovoltaic, photodiode or photoconductive. So in terms of this thermal or uncooled, low sensitivity is there, slow response, no cryogenic cooling required. And in this cooled, they have high sensitivity, fast response and require cryogenic cooling. That is why they are called cooled. Working principle of these photon detectors: photoconductive surfaces. So fabricated from single type of semiconductor, when photons are absorbed by the semiconductor, it generates electron and hole pair like charge carriers. So the increased number of charge carriers lead to an increase in the electric conductivity of the semiconductor. So the change in the electric conductivity, it leads to an increase in the current flowing in the circuit. So hence to a measurable change in the voltage drop across the load resistor, photon gets detected. Right? This is the ohmic contact, this is the incident radiation, and here we can get the signal. Photovoltaic detectors, this is based on photovoltaic effect across a PN junction. So no bias voltage is required. So if the junction is short circuited, current will flow in the circuit when the junction is illuminated. Right? This is an open circuit, also known as this photovoltaic. And solar cells, low dark current, slow response, this is short circuit. Now photodiode detectors, a PN junction with reverse bias voltage is termed as photodiode. So applying a reverse bias across the photodiode increases its speed of response compared to photovoltaic detectors, which we just saw. So however, this large or dark leakage current of the photodiode tends to increase with applied reverse voltage, resulting in an increase in the amount of short noise generated by the photodiode. So in general, a PN junction is operated in the photovoltaic mode when low noise is of prime concern and under applied reverse bias when maximum speed is needed. Materials commonly used for photoconductive or photodiode detector. They are silicon, which is used in the visible, near ultraviolet and near infrared, and germanium or indium gallium arsenide (INGAS). This is for NIR. So visible silicon, NIR silicon, NIR germanium, and in gas. And indium antimonoid INSB, indium arsenide INAS, and mercury cadmium telluride, that's MCT, and germanium doped with elements like copper and gold in the longer wavelength, that is far infrared. So working principle of thermal detectors: absorber means we have absorbers which absorbs IR radiation and converts it into heat energy or temperature change. So temperature change is the main aspect. And then we have transducers. They sense the temperature change and converts into some measurable parameters. So temperature rise, then we have this thermal insulation also. Temperature rise in absorber and transducers. So this temperature change can be computed to some measurable through transducers. Thermopile detectors. This is based on Seebeck effect. So when two dissimilar metals or semiconductors are joined together at each end and both junctions are at different temperatures, a thermoelectric EMF is generated, electromotive force is generated, causing a current to flow in the circuit. The thermopile consists of large number of thermocouples. This is a change in temperature, change in voltage. So it actually transforms the temperature into the voltage or a current. Then we have these pyroelectric detectors. These detectors employ pyroelectric effect to sense the photons. Among the materials that reveal the pyroelectric effect are those whose molecules have dipole moments such as triglycine sulfate TGS, lithium tantalate LiTO3, and polyvinyl fluoride PbF2. The advantages of this pyroelectric detectors is pyroelectric detectors have fast response as compared to the thermal detectors. These thermal detectors, right? And disadvantages is this pyroelectric detector do not have a DC signal. Hence, the surface temperature must be modulated in time by means of a chopper placed in front of the detector. And the applications are pyroelectric detectors are used as a temperature change sensors and in infrared imaging. So, change in temperature, this pyroelectric says change in polarization. Then we have this bolometer detector. Bolometer uses the phenomena of change in resistance of material when the temperature changes. So when IR radiation is incident onto this bolometer, it temperature changes when it turn causes change in the resistance. So the change in resistance is sensed by electrical bias to measure the energy of the incident photon. The bolometer is in circuit in series with a voltage source so that the current flows through it, and as the resistance change, the voltage drop across the element changes and providing a photon energy sensing mechanism. So this is change in temperature, bolometer, change in resistance. Now photodetector performance matrix. This is responsivity. So responsivity is defined as detector output per unit input. So output photocurrent, input optical power. This is responsivity of a detector. Then quantum efficiency is also there. Quantum efficiency is number of electron hole pairs generated by the detector per incident photon, right? So this is given by eta, and it is number of electron which is collected with the ratio of number of incident photons. So electron rate by incident photon rate, this is RE by RP, this is quantum efficiency. So we have this responsivity, means output photocurrent to the input power, optical power, and then we have this quantum efficiency. So for responsivity and quantum efficiency are there to actually detect the performance metrics. These are the performance metrics. Now pixel size, it is the size of a single detector element of the imaging array. So more pixel size means more collection of optical energy, light, and this means higher sensitivity. So but lower resolution means lesser detail. So typically 3 to 10 micrometer of this VIS, visual and NIR detectors, and 20 micrometer of cooled MWIR and WIR detectors, that is medium wave and LWIR. So 17 and 25 micrometer for uncooled LWIR detectors. This is a single pixel, and this is a focal plane array or sensor array. Now we have this fill factor also. This is the ratio of active area to the total area of single detector elements. The fill area is active area by total area. This is the percentage of pixel area that captures photon. Typically 25 to 100%. This is active area, this is the total area. And well capacity is also there. When the ability of each pixel to collect the photo generated elements, right? Ability of each pixel to collect the photo generated elements. So saturation charge 45 to 100 K electrons, and depends on the pixel size, limits dynamic range, and once detector well is filled up, electrons can flow into neighboring pixels. Blooming effect is there. These are the photodetectors for commercial engineering or imaging. Thank you so much. Hope you got a bit idea about